Every even number greater than 2 can be expressed as the sum of two primes. This is the Goldbach conjecture. When the actual solutions for these numbers are plotted, they form a chaotic scatterplot known as the Goldbach comet. For a century, mathematicians have used the prime number theory to analyze this data. They treat the comet as a set of points governed by the statistical distribution and density of primes. In 1923, Hardy and Littlewood proposed an approximation model that draws an average curve through the center of this chaos. The Hardy-Littlewood model assumes that prime intersections occur with the frequency of random coin flips. It tracks the general density of the comet, but its probabilistic nature means it cannot establish a guaranteed lower bound for every individual number. Models built on averages leave open a technical possibility that for some extremely large number, the local count of partitions could fluctuate all the way down to 0, which would disprove the conjecture. A definitive solution to the Goldbach conjecture is impossible as long as the math relies on the pseudo-random behavior of primes. Independent researcher Hedi Zarkuna rejects statistical guesswork. His index theory framework replaces probability with deterministic geometry. He defines absolute space, a rigid combinatorial grid where prime numbers are secondary features of a deeper fixed architecture. Zarkuna's thesis is that Goldbach partitions are the predictable structural leftovers of a geometric subtraction within this space. The proof is modeled as a physical interaction, a linear reservoir of candidate coordinates being reduced by a logarithmic sieve. To solve the problem, we have to measure the physical limits of this coordinate system, rather than the frequency of the primes themselves. The foundation of the model is the Basin operator, B3 of 2n. This represents the maximum volume of candidate pairs before the sieving process begins. Visualize a number line up to an even number, 2n. Fold it back on itself to create coordinate pairs summing to that number, defining the total combination space. The modulo 3 parity selector physically constrains this space, splitting the timeline. When 2n is divisible by 3, the grid allows mixed parities. This case B scenario offers maximum freedom, creating a candidate pool of roughly n over 3. If not divisible by 3, the grid enforces strict parity, halving the space to n over 6. This geometric halving explains the factor of 2 that Hardy and Littlewood manually added to their statistical model. Here, the halving is a direct result of the grid's topology. The rules of divisibility by 3 dictate the starting volume of potential solutions, establishing a floor before the primes are even considered. Zarkuna introduces the deterministic survival function. This is the sieve that eliminates invalid coordinate pairs from the basin. The sieve has two modes of destruction. Strong survival occurs when a prime divides 2n, eliminating only one coordinate. Weak survival occurs when the prime misses 2n, striking two distinct coordinates and destroying twice as many pairs. We can compare these models using the number 540, a value that exposes the inaccuracies in statistical projections. Because 540 is divisible by 3 and 5, the Hardy-Littlewood model applies cumulative statistical bonuses. It predicts 48 partitions, but only 30 actually exist. Zarkuna's model calculates the physical limits of the space instead. It ignores density bonuses and identifies a deterministic floor of 25.4. While probabilistic models can be misled by density illusions, the topological sieve accurately tracks the actual physical floor of the system. To guarantee that a partition always exists, Zarkuna applies a rigorous stress test to find the absolute worst-case scenario for survival. He stops checking for prime numbers. Instead, he sieves the basin using every topological index f of n equals 3n plus or minus 1. This creates a redundant and aggressive filter. It is significantly more destructive than a standard prime sieve because it strikes coordinates regardless of whether the index is prime. If a coordinate pair survives this level of destruction, it is logically guaranteed to be a valid Goldbach prime partition. This massive stress test converts a prime number problem into a mechanical sorting operation with a highly predictable outcome. When this redundant 6k plus or minus 1 sieve is applied, it triggers a chain reaction of algebraic cancellations within the survival equation. The survival product for each pair collapses into this simplified fraction. Multiplying this sequence for every index up to the square root of 2n creates a complex product. To evaluate its limit towards infinity, we apply the Euler gamma function. The gamma function allows us to extract a deterministic constant, k, which is approximately 0.2286. This leads to the final equation for the survival floor, 0.2286 multiplied by n to the power of 2/3. By using the gamma function to solve the telescoping product, Zurkuhne derives a deterministic power law that governs the survival of partitions. The final step is comparing the volume of the basin to the destructive power of the sieve. The combinatorial space of the basin grows at a linear rate, O of n. The maximum destructive power of the sieve is polylogarithmic, O of log squared n. Linear growth always outpaces logarithmic decay. This means the sieve eventually runs out of power to destroy the remaining coordinate pairs. This chart plots the real Goldbach comet. The red line is the statistical average, while the solid blue line is the Zurkuhne deterministic floor. This power law diverges to infinity, crossing the critical threshold of one guaranteed partition at 2n equals 20. Beyond this point, the coordinates provided by the basin always outnumber the cuts made by the sieve. The Goldbach conjecture is a result of this structural imbalance. The expanding volume of absolute space guarantees that a prime partition will always survive.